Today's lecture is on additional properties of normal random variables. And in this section, all random variable considered have finite second moment. Okay. The first topic is about covariance matrix. We define the covariance matrix lambda of n random variables x sub 1, x sub 2 up to x sub n as the matrix formed by possible covariance of random variables in this list. Okay, so the first one will be the covariance of x1 and x1. So that is the variance of x1. The second is covariance x1 and x2. The last one is covariance x1 with x sub n. And the second row is covariance of x2 with each of the random variable in the list. Covariance x2, x2, covariance of x2, x sub n. And the last row is covariance of x sub n with xi's. So the first is covariance of x sub n with x1, covariance of x sub n with x2, up to covariance of xn with itself. Okay. All right. Now, since the covariance of x sub I and x sub j is equal to the covariance of x sub j with x sub I, all right, by proposition 7.4.2-1, the covariance matrix lambda is the covariance matrix of n random variables x1, x2 up to xn, xn n times n real symmetric matrix. All right, and for real symmetric matrix, we have an important result from linear algebra. But before we state that, which is called the real spectral theorem, and before we state the real spectral theorem, we will review a concept called orthogonal matrix. So now an n times n real matrix U is called orthogonal. All right. If U times U transpose equal to U transpose times U equal to the identity matrix. Okay. And it is clear that from these identities, the columns of n times n real orthogonal matrix U form an orthonormal basis for the n-dimensional Euclidean space Rn, and so do the rows of U. Okay. Okay, and so this can be seen from here. So if we expand U, look at the U by their columns. So U1, U2 up to UN are n columns of matrix U, and its transpose becomes to U1 transpose, U2 transpose up to UN transpose. Okay. So when you multiply, oh, by the way, I think I have to write it. This is too crowded. Okay, so, well, okay, okay. Maybe you use row 1, row 2 up to row n. All right, and here, row 1 transpose, row 2 transpose, row n transpose. Okay, it is identity, right? So this is equal to 1 0 0 0 1 0 0 0 1. Okay. So this is the first row of U. Second row of U is set up to the last row of n, and the U transpose becomes to, we have n columns, so that is the transpose of row 1, transpose of row 2, etc. Okay, and so R1 so that okay, so R1 times R1 transpose is just the inner product of the first row and the first column. All right, and so R1 and R1 transpose is equal to 1, and R1 times R2 transpose is 0. So they are orthogonal. So the first row and second row are orthogonal, etc. So different rows are orthogonal to each other, and but the length of each row is equal to 1. Okay, so that's why they form orthonormal basis. Okay, and similarly from this identity, okay, so if here we write down, this is R1, this is U1, U2, UN, that's U, and U transpose becomes to U1 transpose, U2 transpose, UN transpose. So this is equal to 1, 0, 0, 0, 1, 0, 0. Okay. Okay, and so you see U1 transpose times with each columns. For the second column is 0. U1 transpose with the last column is 0. So you can see that different columns are orthogonal to each other. And for each column, U1 transpose times U1 is just the square of the norm of U1, and it's equal to 1. Okay, so they are normalized. Okay. So that is, it is quite easy to see this result. Okay, and so now the real spectra theorem. Okay. The real spectra theorem states that an n times n real matrix A is symmetric if and only if there exists an n times n real orthogonal matrix U, and n times n real diagonal matrix D, such that A can be written as the product of U, D, and U transpose. Okay, and where the diagonal entries of D are eigenvalues of A. Okay. Okay, so that is the real spectral theorem. And from here, we know the covariance matrix of n random variables is an n times n real symmetric matrix. So that's the covariance matrix lambda of n random variables x1, x2, up to xn has a spectra decomposition this is called spectral decomposition U, D, and U transpose. And we can write the detail. So here, U sub i's are columns of this orthogonal matrix U, and the D is a diagram matrix, and the diagram entries are eigenvalues of the covariance matrix lambda. Okay. All right. So where UIs are real, also normal eigenvectors of lambda in Rn corresponding to real eigenvalues lambda sub I, i.e. we have the eigen equation for okay, so we have the eigen equation there. Actually, we can look at the eigen equation from this spectral decomposition. So if you multiply U from the left-hand side on both sides, we know lambda U becomes to U D here. Okay, so that we have lambda U1, U2, UN, and the UD U1, U2 up to UN. This is lambda 1, lambda 2, lambda n, 0, 0. And if when you multiply them, this is equal to lambda 1, U1, lambda 2, U2, lambda n, UN. Okay. Right. And when you apply lambda to each column, you get lambda U1, lambda U2, lambda UN, Okay. Now, then you identify each component, each column. You give the eigen equation. Okay. Okay. And to further characterize the covariance matrix, lambda. All right. Then we will express lambda in the vector form as follows. Okay. So we let mu I to be the expectation of each x sub I, and then the covariance matrix, right? Well, the covariance matrix X. Right? So the first entry, the covariance of x1 and x1, so that is the variance of x1. The second, the 1, 2 entry is the covariance, all right, of x1 and x2 up to okay. And the second row, okay, that is second row up to the nth row is the covariance between xn and each other and each random variable x sub I. It's 2, sorry. 2 here. 2, 1. Okay. Expectation xn un. That. Okay. So you can see that the expectation operator, all right, is applied to the product of two random variable, right? In each entries of the matrix. So now we can, so because they apply the same operator, the same expectation, so we will we'll think about that the same expectation operator will apply to a matrix of random variables. So that this is x1 minus mu1, x1 minus 1. Okay, so this is the first entry of a random matrix, and this is okay, and the second row of the random matrix will be okay, and the last row will be this one. Okay, so the expectation will apply to this random matrix. Means that it applies to every entries, every random variables in this random matrix. Okay. Okay, and as we can see that the random matrix is formed in a particular way. Okay, so we can see that the random matrix is the product of a random column vector multiplied with a random row vector. Okay. And will be written in the vector form. So that would be x minus mu vector times the. So this row vector is just the transpose of this column vector. Okay. Where x is defined to be the random vector, all right, whose components are random variables x of i's, and mu is a constant vector, okay, whose components are means of x of i's. And this, so this is called the mean vectors, vector of the n-random variables x1, x2 up to xn. Okay, so they call the mean vector. Okay. All right, so you can see the covariance matrix now can be expressed, right, in the vector form like this one. Now, for any vector A, A1, A2 in the n-dimensional Euclidean space, we consider the quadratic form A transpose lambda A. Okay, so that would be A1, A2 up to AN, and the lambda. And the lambda, we have a covariance of xi, xj. Okay, so ij. This is the ij's entries of the covariance matrix. Okay, and we have A1, A2 up to AN. All right, so when you expand the product, you will see that this is I1n, j from 1 to n, AI, covariance of xi, xj, and aj. Okay, so that is the quadratic form, okay, of the covariance matrix. Lambda. Okay. Then we will have then the quadratic form. Okay. The quadratic form, if we put lambda as this vector form, okay, and so by linearity of expectation, we can solve these two constant vector into the inside the expectation operator. So this is actually is equal to H. All right. So here is by the linearity of expectation. Okay. And you can see that this one, all right, becomes to, this is the row vector, this column vector. So this is become to a random variable. All right, and this is again a row vector. So now this is a random vector, and you can see these two random vectors are the same. Okay, so that we write this random vector as square, and clearly, so this random vector we call y, and also this is y2, and so this is the second moment of a random variable y. So of course, it will be greater than or equal to 0. Okay. So where y is actually this product, which is equal to, okay, and it's A1, A2, lambda. Okay, so y actually is this linear combinations of xi minus yi. Okay. Now look at here. Equality holds. All right, so the equality holds if and only if y, the random variable y, is equal to 0 with probability 1. Okay, well, we proved that before. And but y, oh, I have to, so that is at x minus mu is 0 with probability 1. Okay? So the quadratic form is 0. All right, it's 0. So equality holds means that t equal to 0. Okay, if and only if that this constant vector a inner product with this random vector is 0 with probability 1. So that this is 0 means that xi's satisfy a linear equation, okay, with probability 1. Okay, so that is important. That is an important observation. Okay. Okay, and so this one specify a linear equation of x1, x2, up to xn. Okay? Okay. All right, so if whenever we know that there is a quadratic form, which is 0 for some constant vector a, then this a will make up a linear equations. All right, a linear equations for the x1 up to xn. So x1 up to xn will satisfy a linear relation. Okay, and so a linear equations there. All right, so now we know something, especially the quadratic form will be non-negative for all vector A in Rn. Okay. All right, so this property related to a concept. So recall from linear algebra. Okay. And n times n real symmetric matrix. Real symmetric matrix A is called non-negative definite. Okay. our non-positive definite. Okay. If the quadratic form A T A of A is non-negative or non-positive, for all vector A in Rn. Okay? So in real case, for a real matrix to be non-negative definite or non-positive definite, you are required that A should be symmetric. Okay, and then you check the quadratic form to see whether the quadratic form is always non-negative or always non-positive. Okay, to justify this matrix, this symmetric matrix A is non-negative definite or non-positive definite. And it is further called positive definite or negative definite. Okay, if the quadratic form is positive or negative for all A not in the zero vector in Rn. Okay. So the name is reasonable because we just check the sign of the quadratic form formed by this symmetric matrix. Okay, so that is. And there is a characterization of so a simple way to characterize the non-negative definiteness or non-positive definiteness or positive definiteness or negative definiteness of a symmetric matrix. Okay. Now, so we will state here a characterization, okay, of non-negative definiteness, non-positive definiteness, non-positive definiteness, and the negative definiteness. Okay, so all these four properties, right, is the following. Okay, so this is a characterization. And n times n real symmetric symmetric matrix A, it's non-negative, definite, or positive, definite, non-positive, definite. The last one is negative, definite. If and only if, okay, if only if the eigenvalues of A are all non-negative or positive, non-positive, negative. Okay, so that would be a very simple categorization. So just look at as we know from the real spectral theorem, we know a real symmetric matrix has spectral decomposition. So it has unreal eigenvalues. Okay, so it has unreal eigenvalues. And you check if all the eigenvalues of A are non-negative, then this matrix A is non-negative definite. If all eigenvalues are positive, then this matrix is positive definite, etc. Okay, so that would be an easy categorization. Okay. And proof as an exercise. Okay. The hint is that use the real spectra theorem. Okay, so I leave the proof for you. All right, and of course you can check proof in any textbook of linear algebra. Okay. Okay, so now from our discussion here, for any covariance matrix lambda, we know the quadratic form is always non-negative. All right, so now it is safe to say that the covariance matrix lambda of n random variables x1, x2 up to xn, right? It's non-negative, definite. Okay. And the eigenvalues of lambda are all non-negative. Okay, so this is an immediate conclusion from our previous discussion. Right. Now consider the case that the covariance matrix is singular. All right? So we consider the covariance matrix is singular. So that because all eigenvalues of lambda are non-negative, and now, so and when lambda is singular, then some of the eigenvalues are zeros, and the others are all positive. Okay, so we let R be the multiplicity of eigenvalue 0 of lambda. Okay, so we may have repeated the eigenvalue 0, and we let R to be the multiplicity. So now it is clear that R will be from 1 to n, and the rank of lambda is clearly is k, which is equal to n minus r.